we're looking at. Actually, 4. We can use these rules. Remember, it has to do with only if it approaches infinity. Okay, if it approaches infinity, if the numerator is equal to the denominator's degree, we take the division of the leading coefficients. So that answer is 1/2. If the degree of the numerator is smaller than the degree of the denominator, the answer is positive or negative infinity. So this is 3 over positive. This answer is positive infinity. The degree of the numerator is less than the degree of the denominator. That's equal to 0. So these answers, and I gave the explanation, is 1/2, positive infinity, and 0. We cannot use this rule because it does not go to infinity. So all we have to do is put in 2. 2 squared over 2 squared is 4 over 4. The answer is 1. I'm not going to answer questions at this point in time. Put a star by it if you have to. Okay? All right. Is a function continuous? A function is continuous if the limit from the left equals the limit from the right equals f of c. The limit from the left equals the limit from the right does not equal f of c. Not continuous. The limit from the left does not equal the limit from the right. Not continuous. The limit from the left equals the limit from the right equals f of c. Continuous. That's my wording I want to hear. Okay. All your derivative tests will go with increasing. F is increasing if, let's start it all over. We have to use position, not F, because it's velocity. Position is increasing where velocity is above 0. That occurs over the interval from here to here. Position is decreasing where velocity is less than 0. That occurs from the interval from here to here. And I'm not going to use all those numbers to speed up the time. Position has a local minimum when velocity changes signs from negative to positive. Never occurs. Position has a local maximum where velocity changes signs from positive to negative. This occurs from here to here. So it's at 30. Position is concave up where velocity is increasing. It occurs from here to here and from here to here. That's where where position is concave up. Position is concave down where velocity is decreasing. That occurs from here to here. Not from here to here, sorry, and here to here. It doesn't occur at 30. Position has an inflection point where velocity changes sign. Don't care if it's positive or negative or not. It's where it changes sign. That position has an inflection point at 30 because velocity changes signs. Take that back. That's wrong. Strike that. This is the first derivative test, right? So, position has an inflection point where velocity changes directions. That only occurs here. There's no change in direction here. There's got to be an immediate change in direction. So that's not true. So make sure you understand inflection point. I said it wrong first. Okay, second derivative test. Concave up, concave down, inflection point. F is, this is F derivative, so let's talk. F is concave up where F double prime is greater than 0. It occurs over this interval. F is concave down where F double prime is less than 0. This occurs from this interval from here to here. F as an inflection point where F double prime changes signs. This occurs right here at t equals 4. Okay, put a star by it, and I can talk once I get through all this. Okay. Differentiability. To show something's differentiable, F has to be continuous, and F prime has to be continuous. So this is not differentiable because F is not continuous. It's that easy. This is not differentiable because F is not continuous. The last one is the tricky one. This function is continuous, but its derivative is not continuous. The derivative is not continuous at C because it has a cost. Don't say it's not differentiable because it has a cost. It's not differentiable because its derivative, the limit of its derivative is not continuous. The limit of its derivative is not continuous at C. Okay? Number six, a function has a critical point where f prime is equal to 0 or f prime is undefined. No more words, no less words. Looking at this, the critical points, and this is called, so we're going to have to call this f or f prime. We're going to have to go with one of them.
It says F.
So if this were f, we'll do it twice, okay? If this is f, a critical point occurs here because the derivative is equal to 0, okay? New problem, brand new problem, got it? Call this f prime. A critical point occurs here and here because f prime is equal to 0. Depends on what you give. And we can talk more about that later. A graph has an absolute minimum. You notice how this is rolling off my tongue. It's not, I'm not even thinking. It's just automatic. That's where it should be closer. An absolute minimum for a graph, just so you understand what an absolute minimum. You have to look at critical points and you have to look at endpoints. Now, an absolute minimum, you look at the critical points, and the critical points that change from negative to positive, that could be a potential absolute minimum. Don't even worry about the positive to negative critical points. You don't test them. So you test the critical points that change from negative to positive, and you test the endpoints in displacement. Whichever has the lowest displacement is an absolute minimum. Okay? So I'm not going to go through this, but I would assume, so just so you understand, if we're doing from 0 to 5, we have to test 0. This is an absolute minimum. We'd have to test 0 and 5 because they're endpoints. We would not test 2. We would not test 2 because that's a potential local maximum. But we have to test 4. So we do the integral from 0 to 5, the integral from 0 to 0, and the integral from 0 to 3. And how do we do that? By via doing areas. I'm not worried about you physically doing the problem, but talking through the problem. Okay. When does a function have an absolute maximum? Just the opposite of what we said. You have to look at critical points and you have to look at endpoints, but you only look at the critical points in which the sign changes from positive to negative. Okay?